Hello dear students. In today's class, let us try to understand the working of flywheel, and we will try to derive an expression for I, the moment of inertia of a flywheel. So a flywheel is a device as indicated in this figure. It consists of a heavy wheel which is joined together with an axis about which this flywheel can rotate. So due to the symmetry of the system, the center of gravity of the system will be along this axis itself. So you can see this is often used along with machinery in order to provide a consistent moment of inertia to this system, to provide consistency to the total working of the system. So here again you can see this is a flywheel, and often the piston is attached to this flywheel to have a consistency and stability in its working. So the moment of inertia is a huge reservoir of the flywheel is a huge reservoir of moment of inertia. So it must have large value of I, from which the machine can take enough kinetic energy, rotational kinetic energy, and can give back rotational kinetic energy without affecting the working of the system. We will try to understand about the application of the moment of the flywheel after a while. So as of now, we will try to understand the basic principles of flywheel. So to calculate the flywheel and its moment of inertia, let us design an experiment. So the standard experiment to determine the I value of a moment of inertia is like this. So this is our flywheel and it has its axis like this. So we attach a thread to this axis, and the thread will be wound around this axis n1 times. So it is as shown in this figure. The thread is wound around this axle n1 times. So in this figure it is 1, 2, 3 and 4. n1 is equal to 4. You have wound this thread 4 times around this axle. And the remaining thread is suspended from this axle with a mass m attached to it. So this is the stable fixed position of flywheel before we start the experiment. We attach a mass to this thread which is wound again around this axle n1 times. Now this mass is suspended from the ground at a height of h. So in the stable point, or before we start the experiment, this mass is at a height h from the ground. So what is the potential energy of this mass? It will be mgh. Its mass is m, its height is h, so it will have a potential energy of mgh. In fact, that is the total energy that we supply into the system. We will talk about that in the derivation part. So let us try to understand more about this experimental setup. So after making this experimental setup, we will allow this mass to move down by rotating this flywheel. So as we set this experiment into motion, this mass will go down due to the gravitational pull, and as it moves down, it will unwind these turns that we have made on this axle, and as a result, this wheel will start to rotate. Now, let us try to write down a standard equation for this setup. So when we look into this system, even though this wheel is making rotations after this mass moves downwards, there is of course some frictional force that is associated with the system. So when this n1 times turns unwinds and this wheel starts to rotate, of course there will be an opposing frictional force that will try to slow down this wheel and finally stop this wheel. Suppose for each rotation that this flywheel makes, W be the frictional force that it faces. Not the frictional force, W be the energy that is lost due to the friction. Or we could say W is the work done against the friction. Per rotation. Per unit rotation. So even though this flywheel is set into motion, into rotational motion, due to this moving down mass, it has to face a frictional force, and as a result it will be losing energy at the rate of W per each rotation. So this is energy or work done. W is the energy or the work done, not the frictional force. So after this mass touches the ground point, this N1 rotations will be completely unwound and the wheel will be completely set into the rotating mode. We also set this mass and its height in such a way that after we release this mass will touch down this ground, and just when that happens, this thread will be completely removed from this axle. So the total length of this thread is set in such a way that from this axle up to this ground, the thread has exact the same length. So just when this thread completes its unwinding, the mass will touch down the ground and the wheel will be in its full rotating mode. Wheel will have its maximum angular velocity because each unwinding will add up to more and more energy of this rotating wheel. Now, after this mass is released from this axle, as we have seen, this wheel will make rotations about this axle, and for each of the rotations that it tries to make, there is some energy that is lost due to friction. So after some rotations, the wheel will come back to rest, which was its initial position. That is actually due to losing of kinetic energy against the friction. So suppose N2 be the number of times the flywheel makes rotations after the M mass is detached and before it comes to rest. So that is denoted by N2. So we have in fact two notations here. One is N1 and the other one is N2. N1 is the number of times we wind this thread around this axle, and N2 is the number of rotations made by this flywheel after the mass M is detached from this axle and the thread is completely detached from this axle, or after the mass M touches the ground, and finally this flywheel comes to rest. Between these two instances, there are N2 rotations made by this wheel. N2 is not a complete number of rotations made by the wheel. Even when this thread is unwinding from this axle, this wheel will be making rotations. So after this thread detaches from this axle, we start to count the N2, and finally when it stops its rotation, we will stop the count of N2. So N2 is actually the count of number of times the wheel makes rotations after the thread detaches from this axle. So this is the experimental part. We will also measure a few more values. We will also measure the time for which this N2 rotations, the time corresponding to this N2 rotations. So when this thread detaches from this axle, or just when this mass touches the ground, both of them happens together, we will start our stopwatch and we will count the N2. When this flywheel stops, we stop the stopwatch, and the duration for this N2 rotations will be denoted as T in the experimental setup. Now, having understood about the basic working of this flywheel, let us try to understand, or let us try to write down the basic equations corresponding to this system. To write down the equation, we use this law of conservation of energy. Which actually states the conservation of energy within a system. So the total energy that was there in the beginning and the total energy that is at the end, this should be equal. So what is the total energy that is being supplied into the system? As you can see, the mass that is attached here, this is actually driving this whole system. This mass going down is what drives the system or what makes this wheel to rotate. So we can say that the potential energy of this mass is the total input energy of the system, which is simply mgh. Now as this mass moves down, it gives out this energy in various forms. A part of its energy will be used up to give kinetic energy for this mass itself. So it is half mv square, where v is the terminal velocity of this mass. V is the final velocity of this mass. So that much kinetic energy is gained by this block or this weight. So the initial mgh energy, a part of it will be used to give some kinetic energy to this mass. The other part will be used to give some rotational kinetic energy to this flywheel, which is simply half I omega square. And some part will be lost within the system due to friction. Now, let us consider the case up to which this thread detaches from this system. In that case, the initial energy was mgh, which is being supplied into the system. That energy is actually dissipating into the kinetic energy of this weight, which is half mv square. Then the rotational kinetic energy of this flywheel, which is half I omega square. And also a part of this energy is lost as work done against the friction. So if N1 is the number of wounds that we make around this axle, and if W is the energy lost per each of the rotation, so just when this thread detaches from this axle, this flywheel will make N1 rotations before that, right? If you are making N1 wounds against this axle, then this wheel will make N1 rotations when this thread detaches, because for each of the unwinding process, the flywheel will be making one rotation. So we can say that during this process, when this M falls down and touches the ground, for each of the rotations, for each of the unwinding process that this thread is making, a W energy will be lost from the system. Since there are N1 rotations like that, we can say that N1 W energy will be lost from the system due to friction alone. So equating all these, I can write the input energy is the potential energy of the weight hanger, weight, which is mgh. That is split up into the kinetic energy of the mass m, the rotational kinetic energy of the flywheel, and finally the energy that is lost from the system as a result of the friction. So this is the equation corresponding to the law of conservation of energy. This was the initial energy of the system that got dissipated into kinetic energy, rotational kinetic energy, and the friction lost due to friction. Now, let us try to find out an equation for this W, which is the energy lost for each rotation due to friction. For that, we will consider the second part of this experiment, where we mentioned what happens after the thread detaches from this axle. We said that this flywheel will make N2 rotations after this thread detaches from this axle or after this N touches the ground. So half I omega square was the initial rotational kinetic energy of this flywheel, and that is getting completely lost during this process. So we have already stated that the flywheel makes n2 rotations during this time. And since during each of the rotation W energy is lost, we can say that during the second half or after the time when this mass detaches from this axle, we can equate half pi omega square with into W. So from this expression, this is also a form of law of conservation of energy. Here we have simply considered a second part of this setup where we consider the rotational kinetic energy of the flywheel alone and how that is getting lost during this n2 rotations, and during each of the rotation it is losing W energy due to friction. So I can write during the second half the law of conservation of energy is half I omega square is equal to into W. So this energy is actually lost due to the n2 rotations. Now modifying this equation, I can write W is equal to I omega square divided by 2n2. Now let us substitute this equation back into equation 1. So substituting 2 in 1, we can obtain mgh is equal to half I omega square plus half mv square plus n1 times W, which is I omega square divided by 2n2. Now let us multiply this equation by 2 throughout. We will get 2 mgh is equal to I omega square plus mv square plus n1 by n2 I omega square. Now let us modify this equation. So 2 mgh minus mv square is equal to I omega square into 1 plus n1 by n2. So here I have taken I omega square as common from this first term and the third term, and mv square is taken to the left hand side of this equation. Now let us substitute for velocity v here as v equal to r omega. So substitute v equal to r omega, where r is the radius of this axle and omega is the angular velocity, maximum angular velocity of this axle or the whole system. So why did we choose r as the radius of the axle instead of this whole flywheel? So this mass achieves velocity v, right? So it is getting unwound from this axle. So finally, when it achieves its maximum velocity, the system will have omega as the angular velocity, and at that time the thread has a radius r, which is the radius of the axle itself. So the mass is attached to this axle, and hence the radius of the axle should be chosen there as v equal to r omega. So let us rewrite this equation in terms of r omega. So we can write 2 mgh minus m r square omega square is equal to I omega square into 1 plus n1 by n2. Now the omega here is actually the maximum angular velocity of the system. That happens when the thread just detaches from this axle and the kinetic energy, rotational kinetic energy of the whole system is at maximum point. From there, its kinetic energy, rotational kinetic energy will slow down, will decrease. So omega is the maximum angular velocity of the system. So the average angular velocity can be written as the mean of the maximum angular velocity and the minimum angular velocity by 2. Roughly, we can state angular velocity, average angular velocity is equal to this value. Omega is the maximum value. So omega by 2 is the average angular velocity. Now let us write down another expression for average angular velocity. So we know during the second half, what we call as the second half of this experiment, we have stated that the flywheel makes N2 rotations. And the total angle covered by this flywheel will be 2 pi into N2. So this much angle is covered by this flywheel, and we have also noted down the time taken for this N2 rotations, which was denoted by T. So we can state that the average angular velocity of this flywheel system is omega equal to the total angle divided by the total time taken, which is 2 pi N2 by T. This expression is obtained from our simple knowledge about the system. This much angle is covered during T time. So let us write down another expression for average angular velocity. So we can state this average angular velocity is also is equal to 2 pi N2 by T. So equating omega by 2 to 2 pi N2 by T, I can write omega to be equal to 4 pi N2 by T. Now we have obtained an expression for omega also in terms of experimentally observed N2 and T. N2 is counted during the experiment as the number of rotations, and T is the time recorded on the stopwatch corresponding to N2 rotations. So now let us rewrite this final expression in terms of the known values. So this is our expression. It is equation number 3. So let us substitute for omega here and here using our final expression for omega, which is 4 pi N2 by T. Substituting 4 in 3, we will get 2 mgh minus mr square into omega square, which is mr square into omega is 4 pi N2 by T, the whole square, which is equal to I into omega square. Again 4 pi N2 by T, the whole square, into 1 plus N1 by N2, into 1 plus N1 by N2. We only have to solve this expression and find out the equation for I. So let us do that. Multiply throughout by T square by 2. So we will get mgh T square minus, here first take the square and multiply by T square by 2. So it is mr square into 16 pi square N2 square divided by T square multiplied by T square by 2, which is equal to I into 16 pi square N2 square divided by T square into 1 plus N1 by N2 multiplied by T square by 2. So as you can see, T square will cancel, this will cancel to give an 8, here again T square will cancel, and here we have another 8. So let us write down the expression for I now. So we have to keep this I alone on this right hand side and take all the other terms to the left hand side. So that is mgh t square minus 8 pi square mr square n2 square whole divided by 8 pi square n2 square into 1 plus n1 by n2. That is equal to I. Now let us again simplify this expression. So cross multiply this into here. We will get, instead of this term, I can write n2 plus n1 whole divided by n2. 1 plus n1 by n2 can be written like that. And 1 n2 term will cancel out. So the final expression will be like this. Also take m as common in the numerator. I can write I is equal to m divided by n1 plus n2. I have taken the mass as common and this n1 plus n2 term as common into gh t square divided by 8 pi square n2. So that is the first term, gh t square whole divided by 8 pi square n2. This is taken as common to the outside of bracket minus 8 pi square r square n2 square divided by, let me write 8 pi square r square n2 square divided by 8 pi square n2. So here certain terms will cancel out, 8 will cancel, pi square and 1 into will cancel. So for the final expression for the moment of inertia will be m divided by n1 plus n2 into gh t square divided by 8 pi square n2 minus n2 into r square. So the various terms in this expression are as said in the experiment itself. Here I is the moment of inertia of the flywheel, m is the mass that is hanged from this thread, and n1 and n2 are two counts. n1 is the number of times we wind this thread around this axle, n2 is the number of times the flywheel makes rotations after the thread detaches. G is the acceleration due to gravity. H is the height at which we suspend this mass from the ground. T is the time taken for this n2 rotation, again n2, and r is the radius of axle. So from knowing these values from the experiment, we can finally find out the moment of inertia of the flywheel. So this is the derivation part of this topic, flywheel. I hope this derivation is clear for you. From this derivation, we can find out the moment of inertia of the flywheel. And I hope the experiment 2 is clear for you. How to do this experiment and find out various terms like n1, n2, t, the radius r. The radius r can be measured using a vernier scale. But so then h should be noted, the mass should be known. And from these values, we can find out the moment of inertia I. So this is the experiment. And now what are the applications of this flywheel? Just like we have seen in this initial figures, flywheels are often associated with heavy machinery to give stability to the system or to give uniform power to the system. Flywheel has large value of moment of inertia, and hence when the system needs more kinetic energy, rotational kinetic energy, it can take enough kinetic energy from this flywheel. It can act like a reservoir. When the system does not need that much kinetic energy, rotational kinetic energy, it can give back. For example, you can see a piston here. This piston is the part of heavy machinery that actually drives these wheels. But this piston may not work properly with regular power if it is alone, because there might be some stable points for this piston where it might get stuck. But when we associate a large flywheel to the system, it will act as a reservoir. It can supply a uniform power into the system. So to make the system work properly, the flywheel should have large value of moment of inertia. And how can you make the value of moment of inertia large for a system? If the mass is fixed, then by making this axis, this radius of the flywheel maximum, you can actually increase the moment of inertia. So the radius of the flywheel, if we intend it to be of very high moment of inertia, then it should have very large radius, just like seen in this picture. So that's about the working of flywheel and the derivation corresponding to its moment of inertia. I hope this derivation is clear for you. Even though it seems a little bit tedious, in fact the concept and the method of deriving this moment of inertia is easy. All we have to do is law of conservation of energy, and you just have to understand what is happening in this experiment to write down these expressions. So just think about all these and try to understand more. Have a nice day. Thank you.